Hello students, today we will see superposition of waves. Vibrations of air column in a pipe closed at one end. Consider a long cylinder tube closed at one end. It consists of an air column with rigid boundary at one end. When a vibrating tuning fork is held near the open end of the closed pipe, sound waves are sent by the fork inside the tube. Longitudinal waves traveling along a pipe of finite length are reflected at the ends as transverse waves are reflected at the fixed end of the string. The phase of the reflected waves depends on whether the end of the pipe is open or closed and how wide or narrow the pipe is in comparison to the wavelength of the longitudinal waves like sound waves. At the close end, there is least freedom for motions of air particles. Thus, there must be a node at the close end. The particle little beyond the open end are most free to vibrate. As a result, an antinodes must be formed little beyond the open end. Mode of vibrations. For fundamental modes, this is the simplest mode of vibrations of air column closed at one end, known as a fundamental mode. Pipe is closed at one end and length of that air column, that is L equal to lambda by 4, that is equal to small l, and A is an antinode and here node. Length of the air column L equal to lambda by 4, therefore lambda equal to 4L, where lambda is the wavelength of the fundamental mode of vibrations. If n is the fundamental frequencies, we have V equal to n lambda. Therefore, n equal to V upon lambda. Therefore, n equal to V upon 4L, that is equal to V upon n into 4 into small l plus E. That is the n correction. For second mode of vibration, we will get here 2 nodes and 2 antinodes and length is 3 lambda 1 by 4. That is small l. So, the next mode of vibration of air column close at one end. If n1 is the frequency and lambda 1 is the wavelength of the waves in this mode of vibrations, then length of air column we will get L equal to 3 lambda 1 by 4. Therefore, lambda 1 is equal to 4L upon 3, that is equal to 4 into small l plus E upon 3. This is the length. So, the velocity in the second mode of vibration, that is equal to V equal to N1 lambda 1. Therefore, N1 equal to V upon lambda 1 is equal to 3V upon 4L is equal to 3V upon 4 into L plus V. Now, V upon L 4 into L plus E, that is N. So, you will get here 3N. For third mode of second overtones. The next mode of vibrations of air column close at one end if N2 and lambda 2, that is the frequency and wavelength of waves in this mode of vibrations, then we will get the length here. That length is 5 lambda by 2 upon 4 and we will get 1, 2, 3 antinodes and 3 nodes here. So, length is 5 lambda 2 by 4. Therefore, lambda 2 equal to 4L upon 5. That is equal to 4 into L plus E upon 5. The velocity in the second mode, velocity in the third is V equal to N2 L2. So, N2 equal to V upon lambda 2 is equal to 5V upon 4L is equal to 5 into V upon 4 into L plus E. That is equal to n. So, we will get phi n. So, V equal to phi n. Vibrations force produced in a string. We have taken one string and length is L here and here we will get the one loop. that is length of that one loop is lambda by 2. Fundamental mode. If the string is stretched between the two rigid supports and is plugged at its end, at its center, the string vibrates. It consists of an antinodes form at the center and nodes at the two ends with one loop form along its length. Means we will get here two nodes and one antinodes. If lambda is the wavelength and L is the length of the string, then we will get length of the loop, that is lambda by 2 is equal to L. So the frequency of vibrating string here is n equal to a small n equal to lambda by 2 and it is equal to n by lambda. So 1 upon V upon lambda, that is 1 upon 2L root T by n. For second mode of vibration, that is the first overtones, here we will get two loops here and length of two loops is lambda 1 and we will get here two nodes and two antinodes and three nodes. Two loops are formed in this mode of vibrations. There is a node at the center and at the center of the string and its both end. If lambda 1 is the wavelength of vibrations, the length of one loop, that is equal to lambda 1 by 2 is equal to L upon 2. Therefore, lambda 1 is equal to small l. Thus, the frequency of vibration is given by n1 equal to 1 upon lambda 1 root T by m is equal to 1 upon n into root T by m is equal to, here we will arrange here, that is 2 upon 2 multiplied and divided by 2. So, we will get 2 upon 2L root T by m, that is root T by m is equal to n. For third mode of vibration, the string is made to vibrate in such a way that here we will get three loops are formed in the strings and the length of the string will be 3 lambda 2 by 3 lambda 2 by 2. Here 1, 2, 3 antinodes will be there and 1, 2, 3, 4 nodes will be formed. If lambda 2 is the wavelength, the length of the loop is lambda 2 by 2 is equal to L by 3. So, lambda 2 is equal to 2L upon 3. Therefore, the frequency of vibrations is N2 equal to 1 upon lambda 2 root T by M is equal to 3 upon 2L root T by M. So, root 3 T by M, 1 upon 2L root 3 by M, that is N. So, we will get here 3N. Beats waxing. Maximum intensity of sound due to the superposition of two sound waves is called waxing. Waning. Minimum intensity of sound due to the superposition of two sound waves is called waning. Bits. One waxing and successive waning together constitute one bits. Bits frequency. The number of bits heard per second is called the bit frequency period of bits. The time interval between two successive waxing and waning is called period of bits. Analytical method to determine bits frequency, y equal to y1 plus y2. So, y equal to a sin 2 pi n1t plus a sin 2 pi n2t. So, y equal to 2a sin 2 pi n1 plus n2 upon 2 into t cos 2 pi n1 minus n2 upon 2 into t. Rearranging the above equations, we will get y equal to 2 cos a 2 pi n1 minus n2 upon 2 t into t sin 2 pi n1 plus n2 upon t into t. Let's 2a cos 2 pi n1 minus n2 upon 2 into t, that is a, and we will get n1 plus n2 upon 2, that is n. So, we will get the equation here, y equal to a sin 2 pi nt. Analytical method to determine for maximum a equal to plus minus 2a and 2a cos of 2 pi n1 plus n2. So, we can get here maximum frequency, that is a cos of 2 pi n1 plus n2 upon 2 into t, that is plus minus a. So, this term is take as a 0 and we will get here t series, that is t equal to 0, 1 upon n1 minus n2, 2 upon n1 minus n2. And thus the time interval between two successive maxima of sound is always 1 upon n1 minus n2. And applications of bit. Phenomena of bits is used for matching the frequency of different musical instruments by artists. They go on tuning until no bits are heard by the sensitive ears. When bits frequency becomes equal to 0, the musical instruments are in unison with each other. The speed of the airplane can be determined by using Doppler radar. Laws of vibrating string. The fundamental frequency of vibrating string under tension is given by n equal to 1 upon 2l root t by m. First law is the law of length, that is n is directly inversely proportional to l because l is here. So the fundamental frequency of vibrating string is inversely proportional to length. Laws of tension, that is n is directly proportional to square root of t. So the fundamental frequency of vibrating string is directly proportional to square root of tension when the mass per unit length are constant. Laws of linear density means n is inversely proportional to square root of m. M, that is the mass per unit length, and it is also called as linear density. So the fundamental frequency of vibrating string is inversely proportional to square root of mass per unit length, that is the linear density, if the tension and the vibrating string are constant here. Homework: explain the phenomenon of production of bits. Deduce analytical the expression for bits frequency of two sound waves having same amplitudes and slightly different frequency. State the laws of vibrating strings. Explain uses of Doppler effect. Thank you.